Hi there. Welcome back to my new YouTube channel, Petrophysics Rocks. Things are starting to go pretty well now. Got a few views on a couple of videos. The residual oil video seems to be the most popular so far, and also starting to get a few comments and remarks in the remarks section down below. So that interaction is really good to see, and I'm happy to encourage you to share your thoughts and any experiences that you have in any similar areas. Obviously, I'm unlikely to go mega viral or hit a great massive YouTube audience, but I think there are enough people out there. I hope there are enough people out there who are curious about scientific stuff and how we make measurements in our reservoirs thousands of feet below the ground. I find it pretty interesting stuff, so hopefully I can connect with a few more. And I guess one of the other things I should probably mention again is that I'm hoping that if you're suitably inspired, you might give a contribution to the Aberdeen Royal Children's Hospital, the Archie Foundation. Just drop them a couple of quid or kronas or whatever it is where you are. If you follow the link down below, underneath you'll see my Just Giving page there. All of that stuff goes straight to the Children's Hospital. They do a great job, and hopefully, whilst I might not go mega viral or make any huge YouTube profits from this, hopefully they'll be able to benefit from some of this information if you find it interesting, and hopefully you do. So as I say, I was trawling through my my website, and obviously I came across this presentation, which is the next one I'm going to transfer up over to here. Now this one is well worth a comment down below, and hopefully even a subscription or two. If you could just press the subscribe and like button, doesn't cost you anything, and it would help me get my message out to a wider audience. This presentation originally on my website was 3 separate presentations, but hopefully what I'm going to do with the miracle of modern YouTube algorithms and editing software is I'm going to combine the applications examples. So I've got the methodology, what I do, how I approach permeability calculations. Permeability is how the rock flows, the ability that the rock has to flow hydrocarbons. And then there are a couple of applications presentations, which are just examples of me using it in kind of pseudo real life, really. There's a few things in there that I'll probably touch on again in the intro to those next time around, just to warn you or whatever. But hopefully you'll find it interesting. So without further ado, let's go on and have a look at flow conditioned permeability modeling, my approach to it. And one of the important things is how we get the oil out of the rock, or gas out of the rock, and how it flows to surface. Okay. Thanks a lot for your attention, and remember, comment down below, give me a like and subscribe, would be much appreciated. Okay, cheers.
I've put this presentation together to illustrate some of my current thought processes on my current approach to permeability modeling. It's something I've been working on for about 12 or so months now, and I think it's proved quite useful to me, so I thought I'd share it with you. So, let's take a routine porosity permeability crossplot. Now, many of you will have seen these types of plots before, but for those of you who aren't familiar with concepts of permeability, you can always check out Chapter 5 of my Petrophysics for Dummies seminar, where the concepts of permeability are explained. But obviously, I think if you're listening to this, you probably have a fair idea of permeability. It's really the conductivity, if you like, the permittivity of the reservoir to flow fluids. So how good is our reservoir rock at flowing fluids? And we use routine phi-k crossplots such as this to predict the reservoir permeability on the y-axis here from a variable that we often calculate, the porosity, the storativity of the rock. So with increasing porosity, oftentimes the reservoir quality increases, and therefore it would be logical to expect that most times the permeability increases too. Now when you first look at this particular crossplot, obviously there's a big splurge of data, and most analysts would at first sight of this would attempt to try and reduce that scatter in some way, perhaps by partitioning this plot into different facies types or different rock types to try and reduce the scatter in this crossplot by some sort of means of some pre-analysis or pre-screening. Now, for the purposes of this presentation, I'm just going to keep this data as a big splurge for now. We'll get on to some partitioning exercises later on, but for now I'd just like to keep it as a big splurge so that I can illustrate some points and some advantages of the technique that I'm going to propose to you now. Okay, so typically if we let Excel do its business and we fit a line through this data, what we're trying to do is we're trying to predict the y variable here, this permeability, which happens to be on a logarithmic scale, from this x variable here, porosity, on a linear scale. And as plots go, this isn't too bad. Clearly there's a lot of scatter about it. I have seen a lot worse on this type of plot, but generally you wouldn't necessarily disagree with that line through that cloud of data. Yes, as I say, there's a big scatter on it, but generally it doesn't seem too unreasonable. Now, one thing I'd like to point out at this stage, and it'll come up a number of times through the presentation, is that this type of technique, this type of plot, is by default what I call a geometric process. Now, some of you will be familiar with the concepts of geometric averaging and arithmetic averaging and harmonic averaging, but when we plot porosity and permeability on this log linear plot, in essence we're doing what's called a geometric process. Now I can explain that a little bit further by, if we go to our Excel help here and look at what a geometric mean is, you'll see that a geometric mean is the product of a string of variables taken with the nth root of those variables. So you've got variables 1 to n, and if you take the nth root of the product of those variables, then that's termed the geometric mean. And in essence, when we take our log linear phi k transform, that's really what we're doing. We've got permeability plotted on that y-axis, and because it's on a logarithmic scale, in essence, when we want to calculate means and regress to means with log linear regression techniques, in essence we're taking a geometric process. We've got a bunch of permeabilities, the logarithms of permeabilities, and when you add the logarithms of permeability together, your school day physics might your school day mathematics, you might remember that when you add a bunch of logarithms together, that is in essence the same as multiplying a string of variables together. So that's this term here. It's the product of these variables is the same as adding these logs together. So when we take means of these y-axis variables, dividing through by the number of samples, for example, again, according to your school day physics, that is the same as taking the nth root of that product. So here we're dividing a bunch of logarithms by this number, and that's the same as taking whatever root it is of those variables. So when we plot a phi k crossplot on a log linear scale, the process that we do to minimize errors, we take this is called a y on x regression. We're really minimizing errors to the logarithm of permeability, and because of what I've just described, that's really a geometric process. Now this will become a little bit more clear later on, I hope. And here, when we're taking a y on x regression, we're trying to take our x value, 10% porosity, and we're trying to predict what permeability that would give us with the least amount of error possible in our y-axis. Now that's not the only way that we can fit lines to these clouds. Excel will, well, you have to fiddle it a little bit, but you can plot a y on x and an x on y regression. So here on the x on y regression, you're coming in with permeability and you're trying to minimize the error in predicted porosity, predicted x value. And there's a thing called the reduced major axes regression, which bisects the two. So there are a number of lines that you might plot through this data cloud. And in fact, if you were eyeballing something like this, if you're a geologist or whatever, you might be tempted to take some hybrid of the two, perhaps the X on Y regression down here, and then maybe swap over to the Y on X up there, just to sort of characterize this slightly banana-shaped cloud. Now, if you're working in cross-plot space like this, how do you know what fit is best? There's a whole bunch of ways that you can determine the quality of fit of these types of lines. There's a whole bunch of mathematical measurements that you can make. You can reduce your residual errors. You can adopt approaches of bi-square fitting. You're taking the least absolute residuals. There's a whole bunch of mathematical stuff there to determine whether you have the best statistical fit when predicting the logarithm of permeability. Now, what I'm going to propose here is that actually I'm not particularly interested in the logarithm of permeability. That's just an intermediate step, if you like, if trying to predict permeability. That's what pays my wages. So all of these mathematical techniques, they're a bit abstract, and do I really care whether an R squared is 0.87 or 0.77? What does that really mean out there in the real world? So what I'd like to do is take our 5K crossplot and pop it down there on the left hand side, just put it down here, and go back to petrophysical roots and take this core data and plot it on a depth scale. So what I've done here is I've taken this core data and I've combined it together on a pseudo depth scale. Now this particular core data set is all the core in a particular field, and I've combined it together on pseudo depths from 0 to 2,000 feet. So I've got 2,000 feet of core data, and I've combined it together in depth as if it were a pseudo well. And in fact, the way that I've combined it, I've put all of one formation up here, then I've put the next formation together here, and the next formation there. So if you like, I'm creating a pseudo well which matches the pseudo stratigraphic column. If you like, this is the geological layers. Here's what's called a Tarbert layer here, an upper Ness layer, a middle Ness layer, a lower Ness, Etive, Rannoch and Broom. And the sharp-eyed amongst you will realize that this is a Brent formation, a typical northern North Sea formation. We have the Broom is for B, Rannoch is R, Etive is E, and the Ness is the N, and Tarbert provides the T, so that's why it's called the Brent formation. And it's quite a nice formation because it has a range of different rock types, different facies types, that give you quite a nice geological contrast, and hopefully it'll illustrate some of the issues that I'm trying to point out quite nicely. So I plot this all together as if it's a pseudo well, and then if it was a well that we actually drilled, a 2,000 foot well, I can accumulate up all the permeability along here, and I can calculate what's called a permeability thickness. Reservoir engineers will be familiar with this concept. I've got 67,000 millidarcy feet here. That's the total footage times the permeability, and that, if you like, gives me the flowing thickness of the rock, or this particular pseudo well. Okay, so with that I can calculate an inflow profile, and this really is the crux of what I'm trying to get across here, is that rather than relying on some abstract mathematical fits, what I'm trying to do is I'm calculating an inflow profile. This is where the rubber hits the road, if you like, from this core data, and then I'll attempt to match the inflow profile with my various regression techniques, and by looking at the flow profile in real time, as it were, I get a real feel for what's important and what's not. So I calculate here, this is an inflow profile. Down our well, this is the amount of oil, in this case, that will flow into this well. Now, how do I do that? If I go here into this little presentation I've got over here, here it comes. We're using what's called Darcy's law. Now, Darcy was a French sewerage engineer who worked on some fountains in France, and he came up with this relationship to describe permeability. That's this K term here. It's a function of cross-sectional area, the pressure drop across things, the length, the flowing length, and this viscosity term here. So I don't want to go into too much detail about that, but to calculate the flow permeativity, you've got a bunch of these constants. Now, if we take our geology Geology oftentimes is quite layered, laid down in water a lot of times, or even by air, and you'll typically see it's quite a layered system. And Darcy's law is originally formulated for laminar flow in pipes. In fact, it can handle some turbulent flow up to about Reynolds numbers of about 10, I think. So it doesn't have to be strictly laminar flow, but primarily we're dealing with Darcy's equation for laminar flow. So if we have a layered system here and we drill a well in it, and then the intersection that well makes with our layered system, we have some flow lines that flow into the well if we apply a pressure drop. So we drop the pressure in the well bore, the well flows into the reservoir, into the well bore, according to the permeability of the rock. So that's all fine and dandy, and I think what I will be stressing throughout the presentation is the importance of arithmetic averaging as opposed to the geometric one that we've already discussed. This is primarily a linear equation, and the flow is pretty proportional to the arithmetic average of all of these permeabilities into the wellbore. So that's one thing that our core plugs that we often take in our wellbore to measure the permeability. We cut some core from our wellbore, and we make these measurements on these plugs. If you like, they're sort of small little tubes in their own right, and therefore what I'm proposing is that this methodology is appropriate. My arithmetically dominated methodology is appropriate for inflow at the wellbore scale, because we've cut our well perpendicular oftentimes to the geology. Now there are, of course, in real life some complications, and of course the geology comes along and spoils some of these nice mathematical relationships. And here I've tried to attempt to illustrate some real-ish geology out here. So if away from our wellbore we might have some cross-bedding features and some laminar features out here, and we have a look at some flow paths out in our wellbore on their way to our wellbore, you might find that actually the wellbore, the flow flows through the reservoir and may get held up by some bounding surfaces or other geological features. So strictly speaking, our permeability is no longer controlled by the arithmetic average of all these beds, but may be dominated by some particular low permeability layers that happen to drape down and block off our flow. And in which case, indeed, a harmonic averaging technique might be more appropriate. Now if you look at your Excel help, again I won't show it here to you, but harmonic averaging involves a bunch of reciprocals. So if you're taking the reciprocal of the permeability, that's the very small permeabilities which have the largest reciprocals, which will tend to dominate the flow behavior here. So you could see a situation where some of these beds out here with their particularly long length scales may not have much of an impact on KH in certain circumstances, but they will certainly have an impact in KV-KH ratio, and in extremis like this, one little layer may dominate the flow profile into your wellbore. So perhaps in certain circumstances harmonic averaging is indeed appropriate. Now, if we take a more harlequin-like a formation, again, I've tried to homogenize this up a little bit. It's a bit tricky to do, but this is just for illustrative purposes. So here in our wellbore, we see we've got some good rock, so some large flows, some poorer rock, some small flows, some combination of the two. So at our wellbore, where we've taken our core and we're measuring our core plugs, we will have a variation in inflow profile, and indeed, my methodology will attempt to characterize this variation in geology at the wellbore. But of course, clearly away from the wellbore, once more, out here in the reservoir, if the flow coming to supply the wellbore has to flow through all of the geology to get there, so the flow is in fact a geometric average, because the flow has to pass through all of the geology to get to our wellbore in the first place. So perhaps some of this near wellbore modeling might be modified away from the wellbore, and again perhaps a geometric average might be more appropriate. However, if we go back to our simple case at the wellbore, I'm kind of assuming that in general, in most cases at the wellbore, the inflow profile is dominated by arithmetic processes, and so therefore an arithmetic approach is generally appropriate for the near wellbore modelling, i.e. the core plugs that we're working with. And if you would like to check out my permeability from cap curve to flow rate presentation, there are some nice examples there of some real PLT data taken across a homogenized formation. So it's a 40 sandstone, so that's a big tank of sand that one might expect to be quite geometric, if you like, but you'll see that there are some high perm streaks in there that correspond very well to the inflow profile from the PLT, which ties in very well with the arithmetic display of permeabilities at the wellbore. So my contention would be that generally let's get the arithmetic permeability characterized at the wellbore, and then perhaps if you think that your geology away from the wellbore is significantly different, perhaps you could investigate that with your various upscaling models. When you upscale your permeabilities to different scales for reservoir simulation, perhaps you could investigate harmonic averaging and harmonic and geometric upscaling there, and maybe away from the wellbore that might handle this geological uncertainty. But for the rest of this presentation, I'll really kind of concentrate on the fact that I think that the arithmetic permeability is the one that really matters at the wellbore. Okay, so we're back here, and so we've calculated this inflow profile. We've made some assumptions about fluid. If I come up here, this is the assumptions that we've made. There's the pressure drawdown that we talked about before. There are some so we apply that pressure drawdown across the sand face. We make some assumptions about the wellbore factors. The effective thickness factor, so I mentioned that if we were perpendicular to beds, we might have every foot that we encounter is a foot of true vertical thickness. But if we have deviated wells, or if our stratigraphy is dipping away, we can maybe discount that by having a TST or a TVD discount factor for our effective thickness at each individual point down the well. We make some assumptions about fluid viscosities. Remember, viscosity was a part of the Darcy equation. And then we make some other assumptions about temperature, and perhaps we can correct for turbulent flow. And then we make some assumptions about formation volume factors and how they relate to fluids downhole and fluids at surface. And then we can calculate an inflow profile. Okay, so this inflow profile here gives us, if it's 110 million cubic feet of gas a day, nearly 31,000 barrels of oil a day, and 49,000 barrels of water a day. And we just calculate that through the assumptions we've made. And if I actually take some imaginary perforation, so here's where we're going to perforate the casing, and we're just going to flow over these perforated intervals. I can calculate a kH thickness for each of these perforations. So I've got 14,000 millidarcy feet here, 6,000 millidarcy feet here, and only about 2,000 millidarcy feet down here. Oftentimes in the lower Brent, the permeability, the deliverability is a lot lower than the upper Brent sequences. So for this set of perfs, I've got 36,000 millidarcy feet. I can calculate a flow rate for each of those perforations. So I'm flowing 6,000 barrels a day here, 2,900 barrels a day there, and only 881 barrels of oil per day there. So overall, from this perforated interval, I'm flowing 16,553 barrels of oil per day. So we'll work with the oil case for now, and that's what the predicted rate from this core data would be. So now let's put our fit line on there. Let's predict what the permeability will be. And now what I'm doing is this red line here is the predicted permeability profile from our Y on X regression that I was talking about earlier on. And here you can immediately see the difficulty with what is in effect this geometric process. It doesn't do a very good job of capturing the inflow profile in this upper Brent sequence, which in these deep Brent reservoirs tends to be dominated by flow from the upper Brent units. And you can see here that while we do a reasonable job down here at the lower permeability end, once we get into the Ness, we're not quite capturing this inflow performance here at all. And that's because a lot of this data up here we're undercooling the permeability. And this is a typical problem when we use this geometric Y on X fit, that we undercool the high permeabilities. Now, I should probably mention here at this stage that one of the other things that we need to do is in situ correct the permeability. What I was doing there was just looking at the raw air permeability data, but obviously when we're talking about downhole well conditions, we've got to correct the core data to in situ flow conditions, and we've got to be flowing fluids through it rather than the air, the nitrogen that's measured, that's put through the core in the lab. So if we make some assumptions about our reservoir depths and pressures and some overburden information, some poroelastic constants, we can make some corrections from laboratory air measurements, with what the core is originally measured at, to our in situ reservoir conditions. And in this case I've used a method, one of my favorites, by a guy called UHAS, and he put together a nice paper, and I'll give you a reference for it at the end, which is quite readable, and it's quite a good, I think, a good first approximation to in situ brine correction. So obviously if you have your own data and you've made your own special core analysis measurements and you have your own correction factors, then by all means use that. But if you don't know anything else, UHAS is a good place to start, and in fact it's always interesting to compare your localized SCAL data with this sort of UHAS empirical approach, and just to make sure, give it a sense check sort of stuff. But we've made some assumptions here about the in situ conditions, and then I've corrected the air profile to an in situ brine profile. So this red line, if you like, is the original air profile, and what I've done here is I've applied this correction, and that's given us this green profile here. And you'll see that up at higher permeabilities, the permeabilities are the same, and as we decrease the permeability, the magnitude of the correction becomes more significant. And then I use that corrected brine permeability to calculate a new flow profile. If I just flick back to the air data, the original core data, you can see that we're flowing 16,500 barrels a day from air permeability over those perforated intervals. If we flick forward to this brine in situ, we've lost 2,000 barrels a day, and we're down at 14,000 barrels a day in situ brine corrected permeability over those perforated intervals. So this is what's called a clean sand methodology. There are various other methodologies as well. UHAS has a relationship for if you have shaly sand, and if we apply to shaly sand here, you can see that all the permeabilities are reduced a little bit, and so a shaly sand gives you a slightly harsher in situ brine permeability, and our flow rate is now down to 10,100 barrels a day. And then also in this particular example, I've got a local empirical trend from my own data, where I've assumed some illite effects in the core that haven't been accounted for in the routine data, so that if I have an illitized zone, the correction, the magnitude of the correction will be even greater, and we're down to 6,900 barrels of oil a day from our core flow profile. But going back to the clean sand trend, we'll just stick back to assume UHAS's clean sand trend with our 14,000 barrels a day flow from the core, okay, over those perforated intervals. And the idea behind this is that whenever we do a regression, in our plot down here on the left hand side, we can see immediately the impact that it has on the flow profiling. So this is the methodology that I'm using to determine whether I've got a good fit or not. So if we predict our predicted flow, at the moment we're at 1,500 barrels a day. So click back, so the core is giving us 14,000 barrels a day, and our current Y on X regression is predicting 1,500 barrels a day. Not too good. So we can try some of those other methods. So here's the reduced major axes plot. Perhaps by eye it might look nicer through this cloud of data, and you can see it does a bit better job. Overall, we're up at 10,950 barrels a day flow rate predicted from this regression. It doesn't look too unreasonable on this cross plot, but you can see where it falls down, over predicting in this lower Brent and still not capturing some of the high stuff in the upper Brent. Now, if we do a X on Y regression, now this is perhaps the line you might draw through by eye. You or a small child might draw that through there, or a reservoir engineer might be tempted to draw that line through that cloud of data and say, well, this is the most important bit of the data, and I want to match this, so I put a line through there. This is an X on Y regression, so here we're trying to minimize errors on the x-axis. It's a much steeper line, and you can see that our resultant predicted flow profile, well, we've certainly increased the flow, 185,000 barrels a day, and you see that the profile goes out to lunch at about this depth. Now, if you can probably imagine that if we were calculating a permeability for these points out here, you can see that our relationship is here. This is 10 Darcys, so probably up here somewhere, these points here, these individual points, are calculating 100 Darcys, and so you have to be a little bit wary that probably some of these points here, we're up over 100,000 millidarcys, so that will obviously have a large impact on any KH calculation we do, and it will shift those numbers quite severely, and obviously it's shifting our flow profile off scale. So the line on an XY cross plot looks quite reasonable, but it obviously has a major impact on our flow profile. Although, having said that, of course, how significant these individual points are has to be taken into consideration. So, one of the things that we like to do, and I was working on some of this stuff back in my Shell days in Oman in 97 and 98, I was trying to look at, when I have large scatters like this, let's have a look at what's the arithmetic average permeability in individual bins. As I've said before, using the geometric method to try and predict permeability tends to underestimate our flow profile. The inflow is often controlled by the arithmetic average permeability. It's a flow profile is in effect an arithmetic process, not a geometric process. So by trying to plot the bin average permeabilities, we can use those and maybe say, right, if that's the arithmetic permeability at each of those bins, what happens if we try and fit a line through those, and maybe that'll give us a better handle on the arithmetic behavior. And in this case, I've used what's called a Delphinier fit, and if you would like to have the reference for that, it's a very readable paper. He's taking bin average data, and in fact he suggests, rather than using the arithmetic average, it's a bit more robust if you use what's called the Swanson average, which basically reduces the effect of potential outliers and gives you a bit more of a reliable or a robust arithmetic mean. But there is the reference. It's a very readable paper, and in fact I think all geomodelers should have a look through there, because there's some very interesting stuff, particularly when it comes to upscaling. And if you look at my second presentation, the applications of some of this, you'll see some of the impact of upscaling that I've sort of investigated with this type of methodology as well. But anyway, so the Delphinier fit, if you like, is a fit through these arithmetic type bin averages, and you can see it does a reasonable job of matching the shape, but it's still, in this particular case, struggling and tending to over-predict, because obviously the permeability of this lower interval here is reasonably significant, but we're still over-predicting overall. So there's another methodology that I'm aware of. My colleague Alan Johnson prepared some stuff for one of our AFES sessions, and in fact I helped him with his presentation with a little bit of this flow profiling work. This is really where I first got the idea of doing this, was to help him demonstrate his methodology, and I've borrowed a couple of slides of his. And let me just borrow them. Seeing as I helped him with it, I don't feel too guilty about nicking them. This was his presentation to the Aberdeen Formation Evaluation Society, and in that it's got a very useful description. He noted that what I've said here is if we take the the logarithm of permeability in a nice log normal distribution. If your data is nicely log normally distributed, and Alan's was, because it was a synthetic data set that he created to make it nice and well behaved and log normal. He noted, and he presents the way that you can, the arithmetic mean is related to the geometric mean by a constant multiplied by the standard deviation. So obviously if you've got a high standard deviation, the spread on this distribution will be quite wide, but he presents the mathematical derivation to get from geometric permeability to arithmetic permeability through this constant multiplier times the standard deviation. And where I helped him present an inflow profile, here you see on this cross plot in his nice log normally distributed data, he's got the y on x regression, and then he's corrected that from the same, we're using the same gradient but with that constant multiplier of the standard deviation, so reflecting the scatter. He's corrected that to a more arithmetic mean. So again, we're all trying to get to the arithmetic mean, because that's what dominates the flow profile. And in his example here, it works really nicely. You see that you've got this predicted core inflow profile, and then his fit, I think, is the green one. Either way, they match quite well. But if you take the standard y on x regression, here you see we were never getting anywhere close to that inflow performance. So again, it's using the same type of methodology and showing that if you look at the inflow profile whilst you're doing this fit, you don't have to just rely on R-squares and correlation coefficients to tell you whether you've got a good fit. And in this case as well, on our big large scatter real data set, which isn't really log normally distributed, it does a better job than my Delphinia relationships, but again it seems to struggle in the same way, over predicting in the poor stuff and under predicting in the high stuff. Now the other thing we can do, because we're doing a flow profile fit, I can do the regression. I can use the Excel solver to say, right, well, what coefficients do I need to match the flow rate? So up here at the top, I know what the flow rate is over the whole interval. I'm predicting from core 25,000 barrels of oil a day. What coefficients do I need to do to match that flow rate with my perm predictor? So that's all I've done here. I've just run the solver and I've come up with a relationship that matches the end result. This can be a useful technique sometimes, but obviously you have to be a bit careful of individual outliers. And here you can see I've obviously matched the result by definition, but here I'm still over predicting the performance of this lower Brent interval. Actually, what I can also do in a similar way is, instead of matching the flow rate, I can actually match the flow profile, if you like. I can reduce the errors in the overall flow profile shape. So I don't worry so much about matching the total rate, but I can try and run the solver to reduce the errors between the two. And in this particular case, you can see I still can't match the dynamic range of the raw data, but that's just another technique, and when we break it down further, I'll show you later that that's quite a useful technique to be able to match the overall shape and not worry too much about individual outliers. Okay, I did mention right at the beginning that if the first approach when you get a scatter like that would be to split things up into their constituent zones. So of course that's what I've done here, and what I've applied here is what I call the Brent zonal fit. And this is probably where this particular crossplot gets a little bit misleading, because this one line is not predicting that inflow profile. In fact, underneath here I have in fact 7 different permeability relationships, one each for all of the main Brent zones that I'm calculating. So here you can see I've got 7 different equations for each of the subzones, and in fact off-piece that's what I'm applying in my spreadsheet to calculate that inflow profile. But in essence I've used the same techniques for each of the zones, I'm using flow matching and Delfinio methods and Johnson methods occasionally to predict the individual zones. But obviously you can see that by splitting it out by zone, as you might expect, you got much tighter fits, still with large dynamic ranges of permeability, so that causes some issues. But I've split the data out into constituent zones and then combined them back together, as I say, off-piste behind on another spreadsheet. There's a lookup table in my data that says, okay, what zone am I in? I'm going to apply the appropriate permeability equation for each of these zones. So in this case then, this front end cross plot becomes a little bit more of an illustrative guide. I can make a bit of a check on it by these purple triangles. What I do is I calculate the overall average permeability for this porosity bin from all of the from all of the 7 permeability equations. So that gives me a rough idea of what the average permeability overall is coming to, and that's what this line is, this pseudo line, if you like, is trying to predict. But you can see by splitting it out into zones, as you might expect, I do get a bit better match. I'm still struggling to match the flow profile in this Tarbert interval. In fact, I've got a much harsher, a very steep prediction line, and it tends to easily over-predict flow profile. But you can see what I'm doing here. I'm trying all the time to match the flow profile, because that's the thing that I'm really interested in, and not really the logarithm of permeability. We can take this a little bit further, and instead of just looking at the major geological zones, we can look at the Fasci space fit, and lo and behold, we get an excellent match here. And why are we doing that? Well, in fact, what we've done is we've gone through and we've split the data, the core data up. The geologist has gone through and split the data up into its constituent fascies. So in a similar way that I had the 7 subzones, I've now got, well, a number of fascies Borer-Perm relationships, and I've split those out individually and done the same fitting for each of the fascies. Now clearly some of these fascies, are starting to lack a few data points, and so you have to be a bit concerned that, okay, is what you're measuring or fitting, is that particularly representative? And sometimes it's not quite as representative as you would like. But in this particular case, I know that these fascies are related to each other. They are a series of lower shore face to upper shore face, fine to coarse grain rocks. So intuitively, I know the relationship I expect between these fascies. With increasing grain size, increasing permeability, I expect there to be a certain relationship, and so therefore I'm reasonably comfortable that even though I don't have as many points as I would like in some of these fascies, they make sense in the context of the other fascies. And so lo and behold, when we apply those individual permeability fascies equations, we get an excellent match. So here we are predicting the low deliverability in the lower Brent and the dominant flow from the upper Brent. And just to show you a couple of other examples from other fields, here's another data set from a similar type of reservoir. If I just toggle between the two, you can see it's probably slightly higher permeability for lower porosity, and here we've got a much more severe banana shape, but here we see the typical profile. In the lower Brent we don't have much inflow, and the flow is dominated by the upper Brent. And here I've just put a routine Excel type RMA fit, and once again you can see we struggle to match the dynamic range in this prediction. But if we use our BRENT subzonal fit, we get a much better match. And as I say, each of these Brent subzones has been fit using these same techniques. Sometimes the flow match, sometimes the Delfinio, and combined together. So underneath, this methodology has been applied, and as you can see, we get a much better match. We've got another field example, another banana-shaped data set, slightly lower porosity again, perhaps slightly lower permeability, and again we've got another RMA fit, and it can't match the dynamic range of the inflow profile. And in that case, we can try and match using the flow match technique, try and minimize the errors between the inflow and the predicted profile, but still it struggles. And again, if we do our zonal fit, we get a much better match than we did. It's not quite as good in this particular field, just to be honest, to show you it doesn't always work. But nevertheless, I guess the idea that I'm trying to get across here is the methodology, assessing the applicability or the goodness of fit of your horoperm transforms with flow profiles, the things that you're really interested in. Okay, so in conclusion, what I'm trying to show you here is that if you define your poroperm relationships with your end product in mind, the flow calculation, that's what most of us are really interested in. So when you're doing your y on x regressions, cross plots, and trying to assess the goodness of fit through abstract things like correlation coefficients and R-squared values, if you're always having an eye on the flow profile, then you really see where the rubber hits the road, if you like, and the geology really impacts on the dynamic behavior under flow conditions. You need to be aware, of course, of the significance of some of those outlier points that I showed, and some of them obviously can have quite large numeric impacts. 2 foot of 100,000 millidarcy prediction can soon have a big impact on your overall KH prediction if you're expecting only a 3,000 or 12,000 foot of millidarcy feet. If you've got 2 points that happen to be 60,000 millidarcies in there, then you're going to have some big offsets. So you need to be aware of that, and the nice thing about the flow profile technique is that you can see that quite obviously, and you can make a judgment as to whether you're going to go with the overall fit and ignore those outliers, or whether you actually have some significant high perm streaks, thief zones that perhaps might actually be a major feature of your reservoir that you need to be aware of. So it really highlights those things, and so this whole process really brings home to you the significance of that stuff, whereas sometimes if you're just looking at a cross plot, you don't get that gut feel for things. Of course, at the end of all this, the reservoir engineer may still need to tweak his history match and multiply things by 7 and divide things by 3, but hopefully if we've started out with the correct air to brine in situ corrections, and we've started out with this flow profile in mind, we're starting out from a much better place. So hopefully any corrections that the reservoir engineer is required to do will be of global nature rather than any local nature. And obviously, as I've already mentioned, this type of exercise really highlights where the high perm streaks are and the effects that they will have in your flow prediction. And so when you're modeling these things in your 3D geological models, you need to be aware of them, and as long as the petrophysicist can, or whoever's doing the log poroperm prediction, can preserve those high permeabilities for as long as possible before we go and put them into the 3D geological model, and then the geologist loses all that stuff in the upscaling. If we can get it in there in the first place, then that's all going to be well and good. And so that sort of touches on my final point. If your petrophysicist gives you a traditional, statistically correct y on x log linear transform, so if you ask him, is this just a log linear y on x regression, and if he says yes, then be very wary. Unless his data cloud is very well behaved and is nice and linear or log linear and is obviously log normally distributed, then you have to be very careful. And even then, obviously, you should be making the types of correction that Alan Johnson recommends in his data, in his nice log normal data. You should be making those type of corrections, because what the petrophysicist is doing, what we're doing when we calculate permeability, is in itself an upscaling process half the time. So it's quite possible that, particularly with y on x log linear regressions, that the petrophysicist will have taken away most of the permeability before it even gets to you geologists and reservoir engineers. So you need to be aware of that, and perhaps be aware of the impact of not having that high perm stuff there in the first place. And in fact, that's probably why a lot of times y on x regression of air permeability data often works in the flow simulator. Oftentimes I've heard stories of poorer perm relationships going straight into the simulator and working without much need for a history match, even though it's air permeability data at surface and it hasn't been brined and in situ corrected. I've got a kind of a feeling or a theory that perhaps that's because if you do a y-on-x regression, you're losing the high perm stuff, and you need as much permeability as you can get after that. Okay, so I'll leave you with some references. These are the references I suggest you start out with. The UHAS and the Devol one are very useful, as I say, to routinely calculate those permeabilities routinely, and then if you have relevant scale data to your particular field, then certainly use that. But it's quite useful to compare it to the UHAS data and see whether your scale data is valid or representative. The Delphinier paper, Pierre Delphinier's paper, is very readable, and it talks about some other upscaling issues, which I'll probably touch on in my next presentation, the application of this methodology. And Alan Johnson's presentations, I think, are still available on some websites. As I say, if you email me, I'll give you his email address, or I'll ask him to get in touch with you, and maybe he can share his full presentation with you too. I hope I haven't committed him to too much there, but thank you very much for your attention.